Hello. I will be giving a presentation on the topic of estimation of distributed concentration of mixed gases using AuAg cluster to the LSPR gas sensor. First, I would like to talk about the background and purpose of the research. In our daily lives, there are various dangers that accompany us. It is very important to develop sensors that can detect such dangers. One of the most useful applications of gas sensor is the real-time visualization of gases. By detecting and visualizing traces of gas, it becomes easier to utilize various information, such as identify the source of dangerous gas. In addition, by mounting these sensors on robots and drones, it will be possible to work in places where dangerous gases are present and humans cannot work. My research aimed to develop an imaging device that can visualize the actual gas flow in real time. Sensors for gas visualization have important elements. These are fast response and recovery and high spatial resolution. The gas sensor that can be said to satisfy these factors is the LSPR gas sensor. The LSPR gas sensor used in this project has several features. Look at the top part of the slide. It has been confirmed that CAM sensor has a response speed that can follow the switching of air and gas at 25 Hz. The LSPR gas sensor has a fast response and recovery speed suitable for real-time visualization of gases. Next, I will talk about the slide below. The sensor can also be made to dimension so that changes in transmitted light can be captured by a camera to visualize the spatial distribution of the gas. Because of these features, the LSPR sensor is suitable for gas visualization. The gas sensor we fabricated this time uses a phenomenon called LSPR. When incident light shines on metal nanoparticles, the free electrons vibrate collectively, causing polarization of the nanoparticles and generating an electric field. When this electric field resonates with the incident light of a specific wavelength is absorbed and scattered. The resonance between the incident light and the electric field varies with the ambient dielectric constant, as shown in the equation. As shown in this phenomenon is called LSPR. This phenomenon can be applied to gas detection. First, when incident light is applied to glass substrate on which gold nanoparticles have been deposited, the resonance wavelengths and transmittance change with LSPR depending on the presence or absence of gas. Since the transmitted light changes depending on the presence or absence of gas, it is possible to measure the presence or absence of gas by reading the change in the transmitted light. This LSPR gas sensor uses the change in optical characteristics for detection. It is suitable for real-time visualization of gases because of its fast response and recovery speed and excellent spatial resolution. The LSPR sensor can measure gases by transmitting light through the sensor and capturing the change in the transmitted light with a CCD camera. The LSPR sensor fabricated this time has an AuAg cluster structure with Ag deposited on the top of AuNPs. This figure shows that the AuAg cluster structure has a response characteristic that varies with the thickness of the Ag. 4 pixels can be considered as one subpixel, and one subpixel can measure the concentration of up to 4 different gases. A sensor with 4 fixed subpixels can be lined up to form a 2D gas sensor. In addition, the 4 fixed subpixels can be turned into continuous subpixels to maximize the information available. Since this sensor uses the entire response characteristic distribution, the information of the sensor can be used to the maximum. Another advantage of using the continuous response characteristics of each sensor for calibration and measurement is that it eliminates the need for detailed control of the sensor itself. Next, the method of estimating the gas concentration is explained. CCD camera is used to capture an image of transmitted light without gas exposure and an image of gas exposure. Next, estimate the density of each subpixel of the captured image divided by an arbitrary number of pixels. For example, let's assume that a 4x4 pixel is a subpixel as shown in the figure. Every 4x4 pixel out of the 2048 pixel of the whole image is separated as a subpixel. The gas concentration for this subpixel is calculated using a linear model. Since we are calculating the density of each subpixel, we are calculating the density of 512 by 512 locations for the entire image. This section describes how to fabricate the LSPR gas sensor. Clean the glass substrate with ultrasonic cleaning. Next, deposit AuNPs with a thickness of 5 nanometers on the cleaned glass substrate. Next, stabilize the size of the gold nanoparticles by annealing at 518 degrees for 2 hours. Next, prepare the silver growth solution. Adjust the ratio as described here. Then, as shown in the figure, immerse the AuNPs substrate in the silver growth solution and expose it through a fluomask to grow silver in a pattern. Two gases, limonene and schistosmon, were used to estimate the concentration. Each gas was placed in a sealed container and the transmitted light was captured by a CCD camera. The concentration was then estimated using a linear model. At this time, we divided the subpixels into 512 by 512 pixels and calculated the concentrations of the 16 locations as a whole. The actual result of the calculation is shown in the figure below, where the XY axis is the location of the gas sensor and the Z-axis is the calculated gas concentration. We can see that the concentration in the center of the image is relatively small, while the concentration outside is relatively large. The average concentration for the entire image was 32% for limonene and 34% for schistosmon. The concentration of the mixed gas can be calculated for each substance. Look at the left of the slide. The horizontal axis of the figure is the brightness value of the transmitted lights when the gas is not exposed. The larger the value, the larger the transmittance, which is the area where the silver has not grown. The thicker the edge film, the smaller the change in transmittance, while the area where the response distribution is larger. 2 is the area where the response distribution is smaller. The regression line for 1 has a larger difference in slope than that for 2, and the magnitude of the response characteristic is reflected in the regression line. The regression line of 1 has a larger difference in slope than that of 2, and the magnitude of the response characteristic is reflected in the regression line. In other words, the larger the response distribution of the 2D LSPR gas sensor, the larger the response characteristics will be. Please see the right of the slide. In the figure, the response characteristics are examined for each area of the divided substrate and the average value of the confidence of determination is calculated. The confidence of determination is the rate at which the regression line explains the underlying data. The larger the area to be divided, the higher the confidence of determination. Once the appropriate response characteristics are obtained, the accuracy can be expected to improve. Finally, I'll talk about the conclusion. AU edge crusher to the LSPR gas sensor were fabricated and characterized in order to visualize distributed concentration of mixed gases. When the response values of multiple points were analyzed, the results of linear regression were different where the response distribution was different. Based on the results of this analysis, which adapt adjustable subpixel pattern by image analysis, we believe that the use of sensors with appropriate response characteristics will enable higher performance gas concentration and distribution pattern estimation. Thank you for listening.